Hello, algebra students. Today we're moving on with our exponent work, and today we're going to be starting with division properties. So the multiplication properties, we had several properties, and the names all kind of blend together after a while. The division properties, I think, are a little bit easier, so today should go pretty well, I think. We're finding quotients of monomials. Remember, monomials means I don't have any addition or subtraction in there. It's just multiplying coefficients or numbers with variables. And then sometimes we'll also find powers of quotients, but that's going to be more like the next lesson. So on your paper for today, or as a warm-up explore kind of an activity, we're talking about prime factorization, just so that we can talk about simplifying and what can maybe cancel out of fractions. So if we're thinking about, for instance, number 1, maybe you remember for prime factorization, sometimes we do this as a factor tree. So if I had 42 as a number, the numbers that multiply to be 42 are 6 times 7, and 6 can be 2 times 3. For 56, that's going to be 7 times 8. 7's a prime number already. Remember, we're just trying to break it down into prime numbers, which means that the only numbers that go into each of the numbers that we end up with is just one in itself. So we've got all prime numbers now at the ends of all these branches, right? So if I would write out for number 1, I'm not even going to write these with exponents to start with. 42 is just 2 times 3 times 7. 56, I've got 3 of those 2, so I know I could write 2 to the 3rd power. I'm just going to write it, though, as 2 times 2 times 2 times 7. And then, thinking about simplifying fractions. We do this, but again, this is the stuff that usually kind of happens behind the scenes. We don't really think about doing prime factorization. I could divide the numerator and denominator by 2, for instance. And I could do the same thing with the 7. That's just canceling out those like factors. And what I'm left with is a 3 on the top, and on the bottom I've got a 2 times 2, which is 4, which means 42 over 56 really can just simplify to 3/4. Most of the time we don't take the time to make these factor trees. Usually I would just say, well, what could I divide the 42 by, and what could I divide by into the 56? And I'm guessing that most people would start with 7, right? So if we had 42 over 56, we could divide both of those by 7. So I would have 6 over 8, and then hopefully you'd realize, oh, I can divide them both by 2 again. I want you to notice that what's really happening here is exactly what we got with the prime factorization, right? Just canceling out those common factors, okay? I don't think that we need to do all 4 of these problems maybe in the video, but 30, if I would make a tree, that's going to be 5 times 6, and the 6 will be a 2 times 3. In case you didn't notice before, I like to put these in smallest to biggest order, so increasing order. So 2 times 3 times 5. The 75 could be 3 times 25. So I would have 3 times 5 times 5. So now canceling out things that match. They both have a 5 that matches. They both have a 3 that matches. I end up with 2/5. And again, if I had just divided both of those numbers by 15, not everybody divides by 15 right away. They'd probably start by dividing by 5 and then divide by 3 after that. You'll get the same answer. So again, just to save some time in the video, I'm not going to do all of those, but I want you to see that prime factorization kind of thing. When we're talking about quotients of powers, so now this is on your paper, you'll have all of these factors. Remember, factors are just the things that are getting multiplied together. So 2 to the 8th, you could write out 8 of those 2's, and 2 to the 3rd, 3 of those 2's. And then we can do some canceling. And I know that pink color that's on there is kind of difficult to see maybe, but like that 2 can take out that 2. And that 2 can take out that 2, and that 2 can take out that 2. And what I'm left with is 5 2's in the numerator, right? So that would be 2 to the 5th power. Now, you could also figure out what 2 to the 5th power is, but I'm just looking at this in terms of powers, looking at what happened with the exponents. I want you to look at the 8, look at the 3. We got 2 to the 5th power. Think about that. We're going to do one more example here. So I've got r's this time. I've got a variable, and I'm going to say, oh, who cares? If it's common factors, we can cancel things out. So writing out 5 of those r's and 4 of those r's, so we can cancel, 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 cancel. All that's left is that single r. Or remember, that would really be r to the first power. I'm hoping that after we did those two, you can see what's really happening with those exponents. Instead of our multiplication exponent rules where we were either adding or we were multiplying exponents, this time when we have the same bases, instead of adding them like we do with multiplying, we're going to subtract them. So 8 minus 3 in the first example gave me my exponent of 5. And with the second example, having, again, variable base, doesn't matter. 5 minus 4 gives me an exponent of 1 when I simplify that. Okay, so that is what the quotient of powers property means. Quotient means dividing. Powers is anything with exponents. So again, this is on your paper. It says to divide 2 powers with the same base, you're going to subtract the exponents. That's what we just figured out. And again, here in the video, I've got this, b to the 12th over b to the 9th. You could write out 12 of those b's and 9 of those b's, and then cancel, cancel, cancel. All that you're going to be left with is 3 of the b's that are going to be in the numerator, so b to the 3rd power. If I look at the second example, and I really wish that there was a little bit more space right here, but again, without writing out all of those w's. I have 6 w's on the top, 2 w's on the bottom. 2 of them cancel out. That's why I do 6 minus 2, and I'd be left with 4. Now, over on the side of your paper, there's a think about it little section that we've got here. It says, what steps would you take to simplify 10 to the 12th over 10 to the 9th without writing out all of those tens? You could have 12 tens in the numerator, 9 tens in the denominator, or you could have 12 minus 9 for your exponent, which is going to give me 10 to the 3rd power. And incidentally, that's 1,000. I hope that you're good with those kind of exponents. Now, on the back of your paper, here's example 1. I've got multiple variables this time. I've got b's and c's. I'm going to say, it's okay. It doesn't really matter. They are going to go slowly through these steps, just like we started with the first lesson. And they're going to say, hey, let's take those b's and put the b's together into one fraction. So I just want to look at this part of it. I'll have to erase it because I'm going to write over that stuff. But I'll have b to the 5th over b to the 2nd. And then for my c's, I would have c to the 7th over c. Or you can always put that 1 in there, right? Now you can see in step 2, that's already there for you, but that's just how we simplify that. Or I should say split it up. And they did the second part. They took this part right here and they said, oh, 7 minus 1, that's what we're going to have for this exponent. So in this first blank, I want to figure out what's going to happen with those b's. I would have b to the 5 minus 2. 5 minus 2 is going to be b to the 3rd power. And for the c's, I'll have c to the 6th power. Okay. Now, again, over on the side of the paper, there's a think about it. It says, why can't I just subtract, like in the numerator, the 5 minus the 7 and the 2 minus the 1, right? We're subtracting exponents. But what I want you to see here is the 5 and the 7, that's the stuff in the numerator. Those do not have the same bases. They don't have the same bases. We can't do anything to simplify that. That's why we have to look at the b's and the c's separately. So I have a couple of example problems. I feel like I skipped a slide, but I guess not. I have a couple of example problems. You've got a lot of space over on the side of your paper. Write these down. I want you to be thinking about all of our rules that we did with our multiplication properties also. So in the numerator on this one, a to the 6th and a to the 3rd would give me a to the 9th power. Same base as we add the exponents. A to the 4th on the bottom. Now, Our rule is we subtract those exponents. And again, you could write out 9a's and 4a's and cancel, 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 and I would have a to the 5th power. Okay. Here's another one. When I start with a fraction like this, I would just start with my fraction bar. This 3 is just going to stay in the denominator. It's just part of the denominator. That's okay. In fact, that's going to be the only thing in the denominator on this one. When I look at my m's, I have m squared on the top, m to the 1st on the bottom. And this is a subtraction, right? How many more 2's are in the numerator? Well, there's 1. Do I need an exponent of 1? No, you can write it if you want to, but you don't need it. When I look at the ends, 9 minus 6 is going to give me 3 extras that are in the numerator. Okay, don't forget, we are just working with fractions. When I see those coefficients, the 3 and the 6, that is not a subtraction. 3 over 6, I can divide them both by 3. That's going to be a 1 on the top and a 2 on the bottom. Now, you can put a 1 on the top, but you don't necessarily have to unless there's nothing else there. When I look at the variables now, p to the 7th over p to the 1st, well, 7 minus 1 is going to be 6 of those p's left in the numerator. For the q's, I have 11 in the numerator and only 1 in the denominator. So for the q's, I'm going to have 10 left in the numerator. And then look at those r's. In a fraction, if you have exactly the same thing on the top and the bottom, they just cancel out. You could do r to the 0 power. We're going to learn about that. But for right now, you know that in a fraction, same thing on the top and the bottom, just like we started with our prime factorization, they just cancel out. Okay, this is the check problem. If you're watching this as a video, you could pause the video and try this out. I'm just going to kind of keep going and talk through this. It does say that assume that the denominator does not equal to 0, and that's it. It also says think about it on the side of the paper. That's because we can't divide by 0, right? If you try to do that on your calculator, if you say any number divided by 0, your calculator's not going to be happy with you. It's a domain error or divide by 0 error on your calculator. It's just not possible. So in this problem now, looking at the a's, the only a's I have are these on the top, right? So in my fraction, that a squared stays on the top. Notice none of these answers have fraction answers, so I'm just going to pretend like I'm underlining this. When I look at the b's, I have b to the 9th and b to the 8th. So there's 1 more b on the top. I don't need a 1. The c's are exactly the same. Cancel, cancel, gone. And then there's 3 more d's on the top. So you should have a squared b d to the 3rd, which is letter D. Here, we're talking about molecules of air. So they're tiny, and there's a lot of them in any space that we're going to talk about. We're talking about a cubic liter of air. So at sea level, there's a certain number, 10 to the 25th, which means a 1 with 25 zeros, really, really big number. But if you're 30 kilometers above the Earth's surface, so really, really high, there's fewer molecules. That's why it's harder to breathe. When you're up higher, there's just less air. So I want to know approximately how many times as many molecules are there at sea level versus in the stratosphere. So I would have 10, I'm going to treat this like a fraction bar, I guess, 10 to the 25th at sea level, 10 to the 23rd up in the stratosphere. Without writing out all those zeros, that's just going to be 10 to the 2nd, which is really 100. There are 100 times as many molecules at sea level as there are in the stratosphere, talking about air molecules. All right, so similar kind of problem. Now this is for your check. Canada's West Edmonton Mall claims to have the largest parking lot in the world. There's 3 to the 9th parking spaces. That's a huge number. You can use a calculator if you want to, but it's really, really big. California has another parking lot that has 3 to the 8th parking spaces. I want to know how many times as many that West Edmonton Mall has. 3 to the 9th over 3 to the 8th. 3 to the 1st, or just 3 times as many parking spaces. Okay, so your worksheet today has all of these kind of problems where we are subtracting exponents because it's division. So if you have any questions, reach out to your teacher.